So there are also a couple of announcements here. And then we'll start with the first speaker, Amit Giveon from Jerusalem, who will talk about from Big Bang to Big Crunch and beyond.
Yeah, I will describe some of the results of work done with Shmuel Elitzur, David Kutasov, and Eliezer Rabinovich. There are many related works on time-dependent background, some of which we heard in this talk. I want to flash here some of the works that are more directly related to issues that I will discuss here. I will consider string propagation in 3+1 time-dependent background, which begins from a Big Bang, then expand to a universe with a topology of a three-sphere, although it is not isotropic. Then it recollapses at a finite time and reaches a Big Crunch singularity. Explicitly, this will be the universe that was considered 10 years ago by Napi and Witten. The attitude that we will take in order to study such a string theory is to use an exact conformal field theory in order to study conceptual questions in backgrounds with singularities of this form, like the question about the nature of the observables in this model, the questions of whether there are pre-Big Bang regimes as well as post-Big Crunch, and if they exist, what is the matching of the wave functions across the singularities. And the organizing principle for addressing these questions will be a quotient conformal field theory. The particular quotient CFT, which has as its background this kind of universe, is the quotient of an SL2 times SU2 group manifolds by a certain U1 squared. And quotients of SL2 as candidates for exact conformal field theory backgrounds, which are cosmological and string theory, were considered by many people. I listed the first few. The particular model that I will consider, as I said, is the one suggested by Napi and Witten. And some of the questions that I raised have immediate questions in this context. First, this particular closed, expanding and collapsing universe is only part of a sequence of expanding and collapsing universes, each connected to the other at their respective Big Crunch and Big Bang. But this is not the whole story. In addition to that, at each singularity, there are whiskers. The whiskers are static, non-compact regimes, which in this particular case behave asymptotically like a space-like linear dilaton theory times some three-dimensional space-time. These static regimes have many problems. In particular, they have closed time-like directions. However, the good side of having such regimes is that they may allow a natural holographic description, a holographic dual of the model, since there is a boundary, and the boundary theory does behave like a space-like linear dilaton, and therefore similar to the suggestion in the work of Aharoni, Berkous, Kutasov, and Zeidberg, there should be a holographic dual description of this model. So I want to study observables in this background. And observables correspond to physical vertex operators in the worldsheet conformal field theory. And in such a theory, there are two kinds of observables. There are delta function normalizable wave functions which correspond to scattering states, and those describe incoming waves from the boundary of the whisker towards the singularity. Part of the wave is reflected, while part of it is transmitted into the closed universe, and then correlated with it, other things happen in the other whiskers as well. In addition to that, there are wave functions which are localized near the closed universes. Those correspond to non-normalizable vertex operators, which are exponentially supported at the boundary. And those are expected to describe the degrees of freedom living in the compact universe. Now, all these modes interact between each other, and to study the interactions in this theory, one has to simply compute the correlators in string theory. And the attitude that I have towards this problem is that string theory computes for us some correlator, and if we want to compute it to the language of quantum field theory in a curved background or to the language of a general relativist, we have to look at the semi-classical limit of whatever we compute, the semi-classical limit of the observables and their correlators, see what it computes for us, and this will be the answer. In the full string theory, it will give us the exact, fully quantum-corrected quantity that we want to compute. So one example that I will try to describe here is the two-point function. This corresponds to the reflection coefficient of the scattering waves from the singularity. There are, of course, many important consistency questions regarding this kind of theories. The first is the consistency of the interaction between the various regimes across the singularity, and one of the results that we have showed that the reflection coefficient is always smaller or equal to 1, so at least it is consistent from that point of view. Generically, it is smaller than 1, so there is an interaction between the various regimes. There is the question of unitarity, and by construction, it is guaranteed that the total incoming flux from the boundary equals the total outgoing flux, so at least from that respect, it is possible that the theory is unitary. There is the question of violation of causality, especially due to the effect of closed time-like curves in the whiskers. But it seems the string theory may be able to take care of that. And then there are the two important questions that were discussed a lot in this conference of the stability and the breakdown of perturbation theory due to back reaction that changes the nature of the singularity. Unfortunately, I will not have any concrete answers to this question in this context. If time will allow me, I may say what I think probably happens here. So in the rest of this talk, I will focus on the semi-classical limit of the model, and I will just show some of the technicalities with the amount of time that I will have that lead to the picture that I advocated about the geometry of the space-time and the nature of the observables. Now, since the guide to this model is SL2, I will present some of the mathematics of SL2 in a way that will be convenient for the particular gauging that I'm going to take. So SL2 elements can be presented by 2 times 2 real matrices with determinant equal to 1. And since I want to gauge a non-compact space like U1 from the left and the right, the U1s that are generated by sigma 3, and which acts on an element G by an exponent of alpha sigma 3 to the left and an exponent of beta sigma 3 from the right, it is convenient to write wave functions which are eigenfunctions of these particular U1s. So by looking more explicitly on the way that the element G transforms under this U1 left and U1 right, it is clear that eigenfunctions with eigenvalues which are exponent of the real numbers m and m bar of this U1 left and U1 right, which I denote by d m m bar, take this particular form. The functions k are to be determined later, but from these polynomial coefficients of A, B, C, and D, it is clear that this function develops non-analyticity whenever one of the 4 components of the 2 times 2 matrix vanishes. So although the SL2 manifold is smooth, I will draw it in a way that distinguish the different regimes where the signs of the 4 entries of the 2 times 2 matrix are different. So for instance, this regime, which I denote by 1, is the regime where A, B, C, and D are plus. When we cross from this regime to this regime, the sign of the entry B is flipped. So this is the this line indicates the 2-dimensional surface along which B equal to 0. And so it is for the other 12 regimes of the SL2 manifold. It is convenient for my purpose to write down the element G as a product of e to the alpha sigma 3 from the left, e to the beta sigma 3 from the right. Oh, sorry. As e to the alpha sigma 3 from the left and e to the beta sigma 3 from the right, and then there is a certain 2 times 2 matrix that sit in between. And in each of the 12 regimes that I left there, this matrix will be different. So for instance, in the region Roman 1, it is this particular matrix, while in the region Arabic 1, it is this one. And so it is for the other regions. And typically what takes us from one region to the other is the insertion of -1s or I sigma 2s in here. What I'm interested in is writing down wave functions in this background. And to do that, I have to consider representations of SL2. Now, there are 2 kinds of unitary representations of the group SL2. Those are specified by the Casimir, which has to be real, or by the spin J, and by an additional number, which is a phase, which gives the representation of the center of the group. So what precisely epsilon is depends on which of the groups we take. I will not get into the details of that here. They're not really necessary for me. And there are 2 kinds of representations. One is the continuous series representation, where J is -1/2 plus an imaginary number. And then there are the discrete representations, where J is an integer up to this epsilon. I will only focus on the continuous representation in this talk. I want to write the representations in terms of eigenvectors of the non-compact space like U1 I'm interested in gauging, of e to the alpha sigma 3, and the eigenvalues are e to the im alpha with a real m. And for the continuous representation, there are actually 2 vectors for each value of m, which I will specify by plus and minus. So in the continuous representations, to summarize, I have states that are specified by j, epsilon, m, and plus and minus. And to consider wave functions in this background, I have to look at matrix elements of a representation of G between 2 such states. So each such matrix element will be specified by non-zero elements. Will have the same J and epsilon for the right-handed and the left-handed states, but they will be specified by the numbers m and m bar. And there will be different wave functions corresponding to the plus, minus, plus, minus. So there are a total of 4 wave functions, 2 out of which are independent in each regime. And in the particular representation I chose for G, we have these obvious exponential factors times a function, k plus minus of the G of theta. Now these functions were computed by Vilenkin, and they can be given in all of the regimes. Just as an example, I wrote down the function k plus plus in the region 1, the region plus plus plus. Here, it takes the form of a product of some hyper-geometric function times the rational function of sin squared of theta times the Euler beta function. Similarly, k minus minus be computed, and it's related to the k plus plus of minus j plus 1, where m and m bar are flipped. This already provides the 2 independent wave functions in this particular regime, and similarly, one can get these functions everywhere. A particularly interesting combination is one which was introduced in a related context more than 10 years ago by Daiger, Verlinde, and Verlinde, which is this particular combination that I call U of K++ and K minus. It has the property that it is infinitely blue shifted at the fiction boundary of region 1, at the b equal to 0 line, where it behaves like b to some imaginary power. And therefore, any normalizable wave packet built out of such mu, u for different values of m and m bar, will have the property that it vanishes on the b equal to 0 line. On the other hand, asymptotically, far away into this regime, this wave function looks like an incoming wave and an outgoing wave with a coefficient, which is the reflection coefficient. Now, the language that I use here is a bit an abuse of a language because in SL2 there are no incoming and or outgoing waves and no reflection, but it is the language which will be appropriate for the physics of the quotient, where this will really be the physics. And the reflection coefficient can be computed, and it's given by this ratio of gamma functions. And for those of you who dealt with correlators in SL2, it is clear that this is the two-point function of primary fields of SL2, specified by spin j and eigenvalues m and m bar, in the limit when k goes to infinity, since I do the semi-classical limit. So if I want to get the precise to all orders in alpha prime correlator, I have to write down the two-point function, which is the precise one. This will pick up another phase, which is k-dependent and goes to 1 in the limit that k goes to infinity. Now, this was only some mathematics of SL2, which will be useful for me when I go to the real problem that I want to consider, namely the quotient. And the particular quotient that I want, well, the string theory I aim to do is, say, the analog of a type 2 string theory in the 4-dimensional background, which is the quotient of SL2 times SU2 mod U1 squared times another 6-dimensional manifold, say a Calabi-Yau manifold that makes it a consistent string theory. This 4-dimensional space is obtained by taking the quotient of G prime, where G is in SL2, the same G that I described before, and G prime is an element in SU2 that I can choose to parameterize by Euler angles. And I want to quotient it by U1 that acts from the left on G and on the right on G prime, and another U1 that acts from the right on G and on the left on G prime. In the language of Napi and Witten, this is the particular case of the universe, which is a sphere at the time that it has the maximal volume. Now, I won't have the time to describe all the details of how to do this quotient. One needs to fix a gauge, and there are several ways to do that. One possible way which is useful here is to choose to fix the gauge completely in the SU2 part, say by setting alpha prime equal to beta prime equal to 0. That by itself does not fix the gauge completely. There is a residual z times z symmetry that has to be fixed as well. And when one does all that, one obtains the quotient conformal field theory. And there are standard procedures in order to obtain the precise background corresponding to this model, which I'm not going to show, but now this is a fake. I don't have anything here. But pictorially, what we eventually get, so we started from this SL2. Now we added an SU2 at each point, but we fixed two of the directions, so there is an additional interval to the 3-dimensional space on this 2-dimensional slice on this transparency, and after doing all the procedure, we are left in one-to-one correspondence with the labeling here. We are left with this picture that I showed in the beginning. So we have a series of expanding and recollapsing universes. Each is topologically a free sphere, and they are connected to each other at the respective Big Crunch and Big Bang singularity, and these whiskers. And just to impress you, I can show you that I can even write down the metric, the antisymmetric background, and the dilaton explicitly. So this, I have to write it separately, of course, in each regime. So this is the background that's so this is the background corresponding to region Roman 1. I also have the background corresponding to the whisker, number 1, and so on. Now I want to study the wave functions in this background. Practically, I already did it. To get the physical vertex operators, I just have to take the product of the wave function, the physical wave functions in the SL2 part, and another one in SU2, which is a familiar wave function in SU2. But since I have to impose gauge invariance of the vertex operators under the U1 square that I gauge, I have to find out what the gauge conditions imply for the quantum numbers. And the gauge conditions are simply that the SL2 quantum number M is correlated with the SU2 spin M bar prime, and so it is for M bar. That means that there is a huge depletion in the number of states of the theory relative to systems we are more familiar with, like strings propagating in ADS3 or in LST, because while in ADS3, in any given J representation, M can take infinite values. In this particular representation, it can take infinite continuous values. While we restrict to the quotient, we only get finite possible values which are bounded by roughly the number of integers of the order 2J prime, the spin of SU2. And that is associated both with the compactness of the universes themselves, as well as with the closed time-like directions in the whiskers. The particular combination of vertex operators, U, that I described before, now has a precise physical meaning fitting the words that I used previously. If I look on a physical vertex operator, which is a combination of k++ and k-, of the form U that I used previously, and then I add to it what is required from the SU2 part with the quantum numbers of SL2 and SU2 correlated such that the full vertex operator gauge invariant, namely the numbers n prime and m are half integers bounded by the spin j prime of SU2, I get a wave function, and the description of the physics of these wave functions is immediately inherited from what I told you from SU2. This describes a wave function, an incoming wave function prepared asymptotically in one of the whiskers, scattered from the singularity, part of which is reflected back into the whisker, and part of which is transmitted into the closed universe. And these vertex operators, which are in the continuous series, of course, interact with the degrees of freedom living in the bulk of the compact universe through the interactions. Finally, I want to remark something about a work that is still in progress with Elitzur, Rabinovich, and Veneziano about the issue of removing singularities in such backgrounds. It turns out that turning on gauge field on this four-dimensional universe, in the language of the quotient, it corresponds to adding a U1 that was there to begin with as part of M6, so the quotient SL2 times SU2 moded by U1 squared times the U1 that I denote here can describe a one-parameter family of the Napi-Witten universes, which are empty. But by taking a quotient where the U1s combine also the extra bluey one that I added here, one can generate a 3-parameter family of backgrounds, which was already considered 10 years ago by Pasquinucci and myself and by Gasperini, Marana, and Veneziano. And these backgrounds describe the same 3 plus 1 dimensional cosmology, but in addition of a 2-component gauge field. If one looks at the structure of the singularity in the presence of this gauge field, one sees that, so when there was no gauge field, there was a Big Bang or Big Crunch singularity at this point, and it was actually connected to a domain wall that goes all along the whisker. And turning on a gauge field removes this singularity towards the whisker. And by turning on a particular large enough gauge field, the singularity disappears completely. What we also checked is that fully reflected uncharged wave functions from the whisker towards the singularity exist if and only if a Big Bang singularity exists from which they are reflected. So I will stop at this point.
Thank you. Any questions?
Thanks. Steve Giddings, Santa Barbara. Where in this picture are the closed time-like curves? Yeah.
Yeah, well, in this picture,
The whiskers. Yeah. Is it all of region 1? Does that all have closed time-like curves?
each such whisker has a closed time-like curve.
Just going around.
Yes.
Okay. Thanks. Well, actually, wouldn't.
like
So,
this.
what are these scattering states? Are well, they're not really scattering states in a sense because of they satisfy periodicity conditions around the whiskers.
Yeah, but although there are closed time-like curves, you don't have to go around them if you don't want. So there is a direction for time to run along the whisker, and they just go along this direction.
Okay.
Gary Horowitz, Santa Barbara. I guess just a comment. I mean, one would certainly expect a very large back reaction, right, in each of your collapsing universes simply for the usual reason. You put any state in there, it has a bit of energy, and when the universe collapses down, the energy gets infinitely blue shifted, causing a very large gravitational back reaction.
Yeah, I guess in view of your talk and the talks by Zyberg and Moore that we heard here, and because of a few similarities of the structure of the singularity, one might expect, it's reasonable to expect that there is back reaction of the kind that you mentioned that will cause a change in the structure of the singularity and perhaps similar physical consequences. However, I should point that there is a difference. This is not an orbifold CFT. Although it has orbifold singularities in it, it also has Wall singularities in the sense that it already has Big Bang and Big Crunch singularities that are not orbifold singularities. Now, the damage that you pointed out is that the orbifold singularities turn into bad singularities, but those are already here. Now, this is not to say that this would resolve the problem, and it is quite plausible that breakdown of perturbation theory would occur here as well. One needs to compute the 4-point function in order to see what would happen, and I think the tools for computing it, we were too lazy to do it, exist due to works of Teschner, Maldacena, Oguri, and others that provide, I think, enough background in order to write down the 4-point function and see if something similar to what happened in the work of Liu, Moore, and Zyberg will appear here. Even if that is happening, I think your optimistic view at the end of the talk could be applicable here, because this theory has a holographic screen, and perhaps if we understand better the holographic dual description of this model, we can say something about non-perturbative effects in this background, even if perturbation theory breaks down. But all that is just what I think about it. Maybe some other people think different things, and there are explicit things that can be checked.